Hello, ladies and gentlemen. So right now I'm going to give this example. Okay, this is an optimization problem, as you know. And let's read it together first so that we know what we're getting into. So the question is, find the dimensions of a rectangle of perimeter 48 that has the maximum area. Okay. Now, they tell us to find the area, the dimensions of a rectangle that has perimeter 48 and that has maximum area. So in any geometric problem like this, my first recommendation is that you draw a picture. Okay, so here I'm going to draw my rectangle. Okay, and what do we know about a rectangle? We know that it has these two sides of equal length. Let's call them the width. Let's call them W for width. And it has these two sides of equal length. Let's call that length, right? Let's call that length L. Now in this case, the condition of the rectangle that is imposed on us by the problem is that the perimeter has to be 48. So in other words, the perimeter is W plus L plus W plus L equals 48. Of course, if you simplify the left-hand side, you get 2W plus 2L equals 48. We can divide both sides by 2, and we get W plus L equals 24. Okay? And so, and then if we want to, and of course we're going to use this right now, we can solve for the width in terms of the length by subtracting both sides by L, or we can solve for the length in terms of the width by subtracting W from both sides. So let's, for our purposes, let's just solve for W in terms of L, okay? Ultimately, it won't make a difference in the end because we'll be able to come back to this later. But before I do that, let me just do that here. So W, so I'm going to subtract L from both sides, minus L, and we get W is equal to 24 minus the length. So let me summarize that here. W equals to 24 minus our length. Okay. So that's one thing that we know. What else do we know about a rectangle that we need to focus on in this problem? Well, they're asking us about the area, right? They want us to maximize the area. So let's see what that tells us. So first of all, what is the area of a rectangle? The area of a rectangle is going to be the length times the width. Okay. And so here we can replace the width with 24 minus L. So this is going to be L times 24 minus L, right? And we can distribute this L, and we can get that the area is equal to 24L minus L squared. And so what is this? This is a function in one variable that describes the area of this rectangle for any value of L, for any choice of the length L. Okay? Okay. And so now we can apply the procedures of calculus to see if we can find the max, to see if there is a maximum area for this particular rectangle. Okay? So let's do that. Now, before we actually solve this particular problem, what I want to do is I want to just recap a little bit about the idea behind the first and second derivative test that we're going to use for this particular problem. Okay? So, for example, if we had some function that looked like this, right, you can see that here, this would be a maximum. You can see that the tangent line at the maximum would be a horizontal tangent line. So that would mean, let's say that this function is called f of x, and let's say at this point, let's call this, let this be the x-axis. Let's say this point is like A. Then the fact that the tangent line is horizontal there means that the f prime of A, the slope of the tangent line at that point A would be 0 to give us the horizontal tangent. And moreover, what I want you to think about for a moment is this. To the left of A, the slopes of the tangent lines are positive. And to the right of A, the slopes are negative. So if I'm going from positive to negative, that means I'm decreasing. So the derivative of the derivative, or in other words, the second derivative at A will be negative. Okay? If the function f has a maximum. And similarly, if we had a function like this, let's say this was f of x instead, then here, which is the minimum, you can see again, we would have a horizontal tangent line. And let's say, just for the sake of argument, that this was also labeled as a here. In other words, the x-coordinate of this point is a, let's say. Then you can see that here, the criteria would be that the f prime of a would be 0, because again, the tangent line is horizontal. But here, notice what happens to the slope. It's negative, and as you go to the right, it turns positive. So if you're going from negative values to positive values, the function is increasing. And since we're talking about the slope of the tangent line is the derivative of the function. So if the slope of the tangent line is increasing, that means the derivative is increasing. That means that the f double prime of a is positive. Okay? So based on this kind of reasoning, what we're going to do to try and find a maximum to our to try to maximize the area of this rectangle, what we're going to do is we're going to find the points that make the a of L 0. I mean, not the a of L, the a prime of L equal to 0, the so-called critical points. So let's copy a of L here. Our a of L, our area in terms of L, is 24L minus L squared. So then my a prime of L is going to be 24 minus 2L, like this. And we can see that if we set that equal to 0, 24 minus 2L equal to 0, I can add the 2L to both sides here. And I get that 24 is equal to 2L. Then I divide both sides by 2, and I get that L is equal to 2L, like this. Okay? So what we just found is that there is a unique value where the a prime of L is 0, namely at L equals 12. So now what we want to investigate is whether the length 12 for the length of this rectangle corresponds to a maximum or corresponds to a minimum of this area function. Okay? Okay. So we know, so what do we know so far? So we know that a prime of 12 is equal to 0. So you can see that that's true in both of these cases. Okay? But how will we know if it's a maximum or a minimum? We will know it's a maximum or minimum based on the value of the second derivative at that point. So let's take the derivative of the a prime of L. Okay? So the a double prime of L, the second derivative of the area function with respect to L, is going to be, if you look at this function, it's negative 2. In this particular case, we can see that the derivative is negative 2 irrespective of the value of L. And so in particular, we know that at this value L equals 12, the a double prime of 12 will be in fact negative. So we know now that a double prime of 12 is less than 0. And we can see that we have satisfied both of the criteria in this scenario, which means that we can say that the area of the rectangle is maximized for L equals 12. Okay? Okay. Now, I just want to briefly point out something else. I know a lot of you, obviously, if you're watching this video, you guys have taken algebra before, and you guys would have said, well, David, like from the moment you wrote this function, a of L is equal to 24L minus L squared, we could have just used techniques from algebra, finding the vertex of the quadratic, to find the maximum. And we know it's going to be a maximum because this is a quadratic that opens downward because the leading coefficient is a -1, the coefficient in front of the L squared terms in this case, right? And of course, I just wanted to tell you that yes, of course, I'm aware of that, and if you observed that, that was great. If you did not observe that, that's okay. But I wanted to make sure that we talked about the calculus part of this explanation, so you guys can see how to use it, and especially when we do other problems where the functions are not so nice, okay? And where we have not developed that rock solid insight of functions that we see, for example, in Algebra 2, okay? Because of course, the quadratic case is like, we know everything about the quadratic case. We can always find the zeros, you know, we can just plug it into the quadratic formula. We can always find the maximum or minimum if they exist. You know, we know everything about those. But when you go into polynomials that are bigger than 2, then there's problems, okay? So in this case, this is like the area function in terms of the length of the rectangle is a quadratic. And so we can apply all that nice, all those nice results from algebra. And I just didn't want to move forward in this problem without letting you know that yes, I knew that, but we're using this example to illustrate how these conditions can be applied to an optimization problem, why they kind of make sense, and so that we could see this in a case that matches, that in a case that we would, in a case that's not too hard to see. And in fact, let's just take that moment here to point out what that would have done if we were to have done it in the Algebra 2 way. That's our quadratic. We know it opens down, as we mentioned before, because the leading coefficient is -1. So we know that our x vertex, or let's say in this case our L vertex, would have been -b over 2a. We know that the b is the coefficient of the L in this case. So that would have been 24. So that would have been -24 over 2 times -1. -24 divided by -2 is +12. Okay, so we would have gotten the L of the vertex to be 12. And that's, of course, exactly what we got by finding the critical point. And, of course, that's no accident. Okay. Yeah, that's no accident. We can talk about that later. But in any case, you can see that if we were using the algebra techniques, we would have also gotten the same value for the maximum and everything else. Anyway, so without further ado, let's summarize the answer to the problem. So here, what we have is we have our rectangle. Let's draw it together. We found that the length was 12. So in our original rectangle, these two had been the L's, the lengths. So we're going to put 12 here on the top and 12 on the bottom. Now, what about the width? What is the width? The width is 24 minus L. Since L is 12, 24 minus 12 is 12. And so we can see that these would be 12 also. And so we can now state conclusively that the dimensions of the dimensions of the rectangle with perimeter 48 that encloses the maximum area is the rectangle with length 12 and width 12, or in other words, the square with side length 12. Okay, this is quite an interesting result, and if you just tweak this argument a little bit, you can see that the following more strong statement can be made, and that is that the rectangle of fixed perimeter with the greatest area will be the square. Okay? Okay. Okay. Now, so now here, what I want to show you, we already finished the problem. We know the answer to the problem and everything. Now, of course, we already solved the problem and everything, okay? But I want to just take a brief moment to talk a little bit about this A of L function. About this A of L function, the 24L minus L squared. Now, if you factor out the L, you can see that you get L times 24 minus L, right? And we already know that that the vertex has x value 12 or L value 12, and if you remember, this is the area function. So the area of 12, if it becomes a square if it becomes a square of side length 12, then the a of 12, then the value there will be 144, because 12 times 12 is 144. So what this basically tells us is that if we were to graph this, first of all, from this factored form, we can see that a of L is 0 when L equals 0, or when L equals 24. So, and it opens down. So it'll look like this. And moreover, here at the middle, when L is equal to 12, we achieve a maximum of 144. So what I want you to think about, so the reason why I'm showing this drawing is I want to kind of like explain one way that you can think about this drawing. And what you can think about it is that here at this top, we actually have the square with every side of length 12. Over here, as we get closer to 24, we have like rectangles that are lopsided, that are like much longer and much thinner. And here, when we're closer to 0, we have rectangles that have length that is very small and that are much taller, because the perimeter is fixed. So that's why they like stretch and deform like this. And so as we move along this curve, the area of these rectangles is, as we go this way, it's approaching this maximum of 144. And as we approach this way, they're like flattening out again. Okay. In this case, they're becoming less and less. They start out super thin, then they get fatter and fatter until they get here, which is the maximum area. Then they start flattening this way as the length gets bigger and bigger. Right? So in other words, what I wanted to show you in this diagram is how this function captures like the areas of these rectangles as their shape changes as a result of the L changing. Okay, and now let's talk a little bit more about what's going on here. Here, what does the AL equaling 0 means that the area is 0. And if you think about it, when we get to L equals 0, that means a rectangle that has no length. So it's basically just a straight line, so it has no area, of course. And by the same reasoning, when L is equal to 24, then you don't have any width for the perimeter to be 48. So you get a flat line that's horizontal, right? And that also has no area. And of course, going below here, going with L's that are with lengths that are below 0 or greater than 24 has no sense, at least in the context of the physical application of this problem, right? Mathematically, we know that this equation will continue downward in both directions, but as far as this problem is concerned, it has no physical bearing. Anyway, I hope you've enjoyed this explanation, and I look forward to seeing you again soon. Thank you so much. You're still there? You're watching this video? Well, I hope you enjoyed it. In any case, if you did enjoy it, well, I encourage you to like it. Put that big thumbs up there. And don't hesitate, and don't forget to subscribe to my channel. And anyway, and also add a comment if you want me to cover some particular topic. I can't make any promises. There's a huge list of topics I already want to cover, but time permitting, I may address that topic. And in any case, I hope you've enjoyed this video, and thank you again.